In this next example problem, we have a car that drives around a flat section of road, and we are asked to make some statements as to whether or not the car skids off the road. So here we have an overhead view of what's going on and then a view of the car moving towards us. And to begin this problem, let's draw the forces and acceleration of the car. If the car is moving in a circle at constant speed, I could say that car will be accelerating in a direction towards the center of the road. So I could draw that picture like this. Here's the acceleration of the car. Now, if we want, we could draw the forces acting on the car. I'll first draw the forces acting on the car from this view of the car moving towards us. So I could say there will be a force of gravity pulling the car down towards the center of the earth. There will be a normal force of the ground pushing back up on the car because the car is not falling through the ground. I call that F normal. And there must be another force because if I project this car to coming towards us, I could say that the car will be accelerating in this direction. So we could think about this. What other forces might be acting on the car? We can't really say the motor produces a force that acts on the car. It's true the car motor is important. It causes the car to go vroom vroom. But the thing is, that's an internal force. So let's think about what happens. The motor goes chug chug, and then parts of the car go vroom vroom, and various parts move. And at the end of the day, the tires spin. So let's think about what happens when the tires spin. If the tires are going to spin, here, let's say we have our tires spinning like this on the road. If you have a very good tire, your tire is going to grip the road, and once it grips the road, it doesn't move. If the road is covered in ice, then the tires will slip. So you don't want the location where the tire is in contact with the road to slip at all. So the tire is going to, at this place right here, the tire is going to try to move to the left, but the tire and the road have a very high coefficient of friction, and so static friction holds the tire in place. The tire is pushing back on the road. The tire is pushing on the road to the left. Now, by Newton's third law, equal and opposite forces, the road must also be pushing on the tire. So the road will push on the tire to the right, and this is the force that causes the car to move. This is the force that causes a car to move in a linear fashion if you're trying to go forward backwards. But if you are turning, the force that causes your car to turn is still going to be the force of friction. The car is physically in contact with the road. The tire is pushing on the road. The tire will cause the car to change its direction. So it is the force of friction that causes this acceleration. And in this overhead view, I could draw the force of friction to look something like this. Force of friction. Now let's see if we can make a statement about the force of friction and what must be necessary to prevent the car from skidding. So I see the force of friction as the only force acting in the x direction on this picture down here. So I could say F net x equals max. I'm setting up Newton's second law in the x direction over here. Normally, I would write out the components of all the forces acting on the car. I would set a lot of them to be equal to 0. I have a 0x component of normal force, 0x component of gravity, 0y component of acceleration. But we've done that a lot before, so for the purpose of this video, I'm going to skip it. However, when you're actually working through problems, it is a good idea to do that. Now, the force of static friction, I could write force of static friction is equal to the coefficient of static friction times the magnitude of the normal force. And static friction, in this case, we are normally we would say static friction is less than or equal to this much, but we want to consider the case where the car is barely not sliding off the road. So in that case, I want to set static friction to be as big as possible where the car is barely hanging on and not sliding off the road. I set static friction equal to mu times F normal. So I could write the force of static friction as mu times F normal. I have no other forces in the horizontal direction, plus 0, and that's equal to the mass of the car times the acceleration of the car. And I'll write that as ma for the moment. I'm going to skip some space here because I'm going to write a few more lines. If I look at the forces acting on the car in the y direction, I could write F net y equals ma y. Now I have the normal force pointing in the vertically upward direction. Gravity is pulling the car downward with a strength mg. And the car is not accelerating in the vertical direction at all, so ay is just going to be equal to 0. So I could set that equal to 0. From this equation, I find the normal force acting on the car in this scenario is equal to mg. And if I take this equation for the normal force and bring it up there, I could say the coefficient of static friction times mg is equal to ma. Okay, let's see what we could learn from this equation here. So I could notice first that the mass of the car cancels on both sides, so it turns out we don't need the mass of the car to answer this question. And I have a number for mu sub s, the coefficient of static friction. I have a number for the acceleration due to gravity, that's 9.8. So I could write this as mu sub s times g equals v squared over r. Now, this is the limit where the car is barely not skidding off the road. So this speed is the fastest the car could possibly move without skidding off the road. That's how we set up this problem. So whatever speed this is, when I plug in 0.7, 9.8, and r, that will be the fastest the car could possibly move without skidding. So I could plug in 0.7 for the coefficient of static friction. I have 9.8 for my acceleration due to gravity. That's equal to v squared over 25. And when I send these numbers to a calculator, I find that the fastest speed the car could move without skidding is 13.1 meter per second. Now, at this point, we have solved part B of this problem. Part A, if the car moves at 11 meters per second, well, it's moving slower, so the car also will not skid there. C of this problem, we are going to consider that the car continues to drive, and then the car encounters a circular section of the road again that again has a radius of 25 meters. But this time, the road is a frictionless surface. So you can imagine the road is covered in ice or something. Now, even though the road is frictionless, the car could still travel around this curve because the road has a banking angle to it. So the road is tilted relative to the horizontal. If viewed from overhead, the road would just look like a circular path, something like this. So you could draw the car driving along, maybe driving something like this. But if you see the car coming towards you, you would see a picture something like this. And we want to ask the question, at what angle should the road be banked to allow the car to move at a speed of 13 meters per second such that the car does not slide down the road? Normally, because the road is said to be frictionless, if the car is just stationary, the car will just slide down to the center of the road, but we don't want that. So to answer this question, let us draw the forces and the acceleration of the car. When I look at the overhead picture first, I see the car moving in a circle at constant speed. That tells me the acceleration is going to be towards the center of the circle. I will draw that vector in. Now, from this perspective, with the car coming towards us, towards the center of the circle would be horizontally to the right. So the car's acceleration is going to look something like this. Now, if I wanted to, I have the speed of the car, the radius of the loop about which the car is driving. If I wanted to, I could calculate the magnitude of this acceleration vector and get a number, but I'm going to put that off for the moment. What are the forces acting on the car? Well, we know gravity is still going to be around, so I could draw the force of gravity pulling the car straight downward. So here is the force of gravity. I know that the car is in contact with the surface, but the car is not falling into the road. So the force of the normal force acting on the car is going to look something like this. The normal force is always going to be perpendicular to the surface, so the normal force is going to look something like this. Now we could ask a question. Are there any other forces acting on the car? Well, there's no string or rope in this problem, so there's going to be no tension force. We already accounted for gravity and the normal force. We said the road is a frictionless surface, so there are no other forces acting on the car. The acceleration, this inward acceleration, will be entirely due to part of the normal force. At this point, we will set up an XY coordinate system and break these vectors into their components. Now, usually when we have a problem with a ramp or some type of incline, I say we should have the x-axis lie along the incline and the y-axis be perpendicular to the incline. I'm going to draw that for this problem as well. So my x-axis will point something like this, and my y-axis will be pointing perpendicular to the road, something like this. Now, I said usually this coordinate system is more convenient to work with. It turns out that for this specific problem, this is a less convenient coordinate system to work with than normal. However, I told you if you see an incline, use an inclined coordinate system. I'm going to follow that rule just for consistency. But if you want practice, you could try solving this problem with x-axis pointing to the right and y-axis pointing vertically upward. At the end of the day, you will get the same results. You'll just have different components for the vectors in this problem. So let us write out the components of these vectors. I'm going to clean up my picture a little bit. I could draw the acceleration vector to look something like this. I notice that whatever angle theta makes with the horizontal and the incline, this angle will also be theta as well. And I know that the acceleration is horizontally towards the center of the circle. If the acceleration is horizontally towards the center of the circle and gravity points straight down, then the angle between the acceleration vector and the force of gravity must be 90 degrees. Therefore, this angle between the x-axis and the force of gravity must be 90 minus theta, because these two angles have to add up to 90 degrees. Let's draw this picture again on a new XY axis where it could be cleaned up a little bit. So I could say here is the Y axis and here is the X axis. I have the car at the center of this diagram. So we have the normal force pointing entirely in the Y direction. I could draw that. F normal. we have the force of gravity that lies at an angle 90 minus theta below the positive x-axis. The force of gravity is going to look something like this. And we have the acceleration of the car. The acceleration of the car is an angle theta above the positive x-axis. Another way you could see this angle being theta, whenever you have two parallel lines, and then you intersect these lines, this angle must be the same as that angle. That's the same picture you have for theta and theta over here. So I could draw the acceleration to look something like this. Also notice that the angle between the acceleration vector and the force of gravity vector must be 90 degrees as well. So we know this angle is going to be theta. This angle will be 90 minus theta. And of course, this angle here will be theta again. So I'll give this one 2 lines. Let us now write these vectors in their components, and we'll actually calculate the acceleration of the vehicle. So the acceleration of the vehicle is going to be v squared over r. It is moving in a circle at constant speed. So I could write a is equal to v squared over r. That is going to be 13 squared divided by 25. And if I put these numbers in a calculator, we find the acceleration of the vehicle is 6.76 meters per second squared. So if I wanted to, I could write the acceleration of the vehicle equals 6.76 cos theta in the x direction, and acceleration of the vehicle in the y direction will be 6.76 sine theta in the y direction. Now I will write the components of the normal force in the x and the y direction. I could write F normal in the x direction will be 0. F normal in the y direction will be the entire magnitude of the normal force, whatever that number happens to be. In this problem, it turns out we won't even need to calculate what F normal is, and you'll see why when we begin calculating it. For the force of gravity, the magnitude of the gravity force is always mg. Now, if gravity points in the negative y direction, which is true for most scenarios we encounter, then I could say gravity has an x component of 0 and a y component of negative mg. However, remember from inclined planes, when we deal with tilted coordinate systems, the force of gravity will have an x component and a y component. The total magnitude of the force of gravity is equal to mg, but we then break up that total magnitude into x and y components. So how do we want to think about the force of gravity? Let's write the force of gravity in this form. Let's draw the force of gravity vector as a right triangle. So here is a right triangle. Let us say this angle here is theta, just like over here. Now, let's say this hypotenuse of this right triangle I drew has a total magnitude mg. Based on what I know from trigonometry, I could say if the hypotenuse has a magnitude mg, then the horizontal leg of this right triangle will be of length mg sine theta, and the vertical leg of this right triangle will be of length mg cos theta. all I did in this right triangle is I made a relationship between the side lengths of the legs of this right triangle and the hypotenuse. I said the hypotenuse has a length mg, therefore the two legs must be of this length. Remember, when you work with sine, sine is defined as opposite angle over hypotenuse. Because the angle I considered is up here, the horizontal leg is going to be sine, and the vertical leg will be the adjacent side to the angle, the cosine side. Now, making up this right triangle was not just a random guess. It was inspired because the hypotenuse of this right triangle is the same as the magnitude of the force of gravity acting on the car. The size of the horizontal leg of this right triangle will be the same size as the horizontal component of the force of gravity. And the total size, the total amount, the total magnitude of the vertical leg of this right triangle will be the same size as the vertical component of the force of gravity when I write force of gravity as a vector. I am intentionally choosing to use the word the size of the vertical leg of this triangle and the size of the component of this vector because I'm not yet making a statement should it be positive or negative. But we look at this force of gravity vector and we could very clearly see it's in the fourth quadrant. I expect the x component of the force of gravity to be positive and the y component of the force of gravity to be negative. So if I want, I could write the force of gravity has x and y components as force of gravity in the x direction is equal to mg sine theta, and force of gravity in the y direction is equal to, it will have a size mg cosine theta, but because we're in the fourth quadrant, I expect this term to be positive and I expect this term to be negative, so I put that negative sign there by hand. Now, at this point, we are going to find out at what angle should this road be banked such that the car could move at this speed without slipping up or down the road. If you move too fast, you'll slip up the road and fly off the outside part of the road. If you're not moving fast enough, you'll be gradually sliding down towards the center of the road. And if you move at just the right speed, you'll be able to navigate the road without slipping up or down. In this case, at what angle will 13 meters per second be that magic speed that you need? So I'm going to set up Newton's second law, and let's look at the x component of Newton's second law first. So I could write F net x equals max, and let's add the net force in the x direction together. Normal force and gravity, I have 0 plus mg sine theta. On the left-hand side, that accounts for all the forces acting on the car in the x direction as I drew my coordinate system. In the right-hand side of Newton's second law, I have the mass of the car, and AX is 6.76 cos theta. 6.76 cos theta. Now I look at this equation as it's written. I notice I have m on both sides, so I could cancel it. I could bring g, the acceleration due to gravity, to the right-hand side. I could bring cosine to the left-hand side. So I could write this as sine theta over cosine theta is equal to 6.76 over 9.8. And I recognize that sine over cosine is just tangent. So I could write this as tangent of theta equals 6.76 over 9.8. Now at this point, you all know how to find the angle from here. You take the tan inverse to both sides, and you find that the angle at which the car could move at a speed of 13 meters per second without slipping up or down is 34.6 degrees.